Okay, I want you to picture a house. It's a nice house.
Hmm.
We're talking uh, modern Scandinavian architecture, minimalist design, fiber optic internet,
The whole 9 yards.
the whole 9 yards. Really good coffee brewing in the kitchen.
Yeah,
But there is a catch.
there is always a catch.
This house is parked on top of one of the most geologically, well, unstable places on the entire planet.
Hmm.
We are talking about a place where the ground literally tears itself apart.
By about 2 centimeters every single year.
It sounds like the setup for a disaster movie.
It does, or maybe a stress test for an architect. But what you're describing is a very real, functioning, high-tech society.
Exactly. Today, we're doing a deep dive into Iceland. But we aren't just looking at those moody travel photos of the Blue Lagoon or, the Northern Lights.
No.
We are looking at the how. How does a modern population actually coexist with a landscape that seems, actively trying to destroy it?
It's quite the paradox. Usually we view natural disasters as these rare, catastrophic interruptions. A hurricane hits, an earthquake strikes, and everything stops.
Right. Normal life is paused.
But in the documents we've analyzed for this deep dive, and we have a stack here, from Institute of Earth Sciences reports to case studies, one thing becomes very clear. In Iceland, disaster isn't an interruption. It is the baseline.
That is the mission for today. We're going to look at the engineering, the economics, and honestly, the sheer audacity of it. There's a section in these notes about fighting a volcano that I'm still trying to process.
You mean the fire hoses?
The fire hoses.
Okay.
Who looks at a fissure spewing molten rock and thinks, you know what this needs?
I need a water pump.
Exactly.
It sounds completely absurd, like something a child would invent. But as we'll see, that moment, that specific decision, it changed how the world thinks about disaster management.
Okay, but before we get to the hoses, we have to understand the problem.
We need to look at the engine driving all this chaos. Because Iceland isn't just a volcanic island. Geologically speaking, it's a freak occurrence.
The reports call it a double whammy, which I'm guessing is not a technical term.
It's surprisingly accurate, actually. To get it, you have to visualize the floor of the Atlantic Ocean. Running right down the middle is the Mid-Atlantic Ridge.
The boundary between two massive tectonic plates, the North American and Eurasian plates.
Correct. And they are pulling apart. It's a divergent boundary. Think of it like a conveyor belt moving in opposite directions.
And as they drift apart, magma rises up to fill the gap.
That's standard geology that happens all along the ridge, but usually it happens deep, deep underwater.
So if that's all it was, Iceland would just be another underwater mountain range.
Exactly. So what makes Iceland rise above the waves? That's part 2 of the double whammy. It sits directly on top of a mantle plume.
Hotspot.
Yes. Imagine a blowtorch, a massive upwelling of hot rock rising from deep within the Earth's mantle, and by sheer coincidence, it's aimed right at the spot where the plates are ripping apart.
So you've got the crust tearing open from the side, creating a gap, and at the same time, this superheated column is punching up from below.
Precisely. And that combination, it produces something like 4 times as much magma as you would find anywhere else on the ridge. That is why Iceland exists. It's a country built on an excess of magma.
And when you look at the map in the source material, it really does look like the island's been slashed by a giant claw. These angry red zones cutting right across the country.
Those are the volcanic zones. And the structure is important here for understanding the risk. You have 2 types of trouble, really. First, the central volcanoes.
Your classic mountain with a crater on top.
Right, a caldera. The magma sits there, it evolves, gets stickier, and can become quite explosive.
And then radiating out from those mountains, you have the cracks.
The fissure swarms, these can be dozens of kilometers long. When these open up, you usually get basaltic magma. That's the runny, glowing red lava you see on the news. It's effusive, it flows.
So explosive mountains and leaking cracks. But here's where the Icelandic recipe gets messy. It's not just fire, it's named Iceland for a reason.
And that is the variable that changes the physics completely. About 10% of the island is covered in glaciers. And our data shows that about half of all eruptions in Iceland happen under that ice.
This is where it gets terrifying. Magma at over 1,000 degrees Celsius hitting a solid block of ice.
It creates a phenomenon called a Jökulhlaup. That's the Icelandic term for a glacial flood.
And we aren't talking about a little snow melt.
No. The heat melts massive amounts of water instantly. But here's the kicker. The weight of the glacier on top creates a lid. The water can't escape.
So it's trapped.
Trapped between the ground and the ice, building immense hydraulic pressure until it finally bursts.
There was a case study in the notes on this. the Gjálp eruption in 1996.
That is a textbook example. It happened under about, 600 to 700 meters of solid ice. The eruption melted more than 3 cubic kilometers of ice.
I want to pause on that number. 3 cubic kilometers. That's a hard number to visualize.
Think of it this way. It's enough water to fill about 1 million Olympic-sized swimming pools.
1 million pools melted.
And it didn't release right away. The water flowed under the ice and pooled in a sub-glacial lake. It sat there for 5 weeks.
Like a ticking bomb.
Waiting. Scientists knew it was there. They were watching the lake levels rise. And then the pressure became too much. It lifted the ice dam and it released.
What was the flow rate?
The peak flow was approximately 50,000 cubic meters per second.
50,000. For perspective, isn't that more than the Amazon River?
It's comparable to the Mississippi during a major flood, but appearing out of nowhere. It wiped out a major bridge, severed the country's ring road, turned a dry plain into a raging ocean.
But the report mentioned that despite that violence, no towns were destroyed.
And that's the benefit of historical knowledge. The floodplain where that water went has been uninhabited for centuries. They know the lay of the land, they know where the water goes, so they don't build there.
They give the volcano its space.
Exactly. But sometimes you can't give it space. Sometimes the volcano knocks on your front door, which means we have to talk about Vestmannaeyjar.
The 1973 Whammy eruption. This is the story.
If you want to understand Icelandic resilience, this is it.
It reads like an action movie script. January 23rd, 1973. A 1,600-meter-long fissure opens up on the island of Whammy, and it's only 300 meters from people's living rooms.
And this wasn't an empty floodplain. This was a town of 5,000 people. Crucially, a vital fishing hub. The lava wasn't just threatening houses, it was moving toward the harbor mouth.
And if the harbor closes,
the island dies. The economy was entirely dependent on that harbor. If lava sealed it off, the town would be uninhabitable.
So, faced with this, they made a decision that sounds, frankly, insane. They decided to fight the lava.
It had never really been tried before, not on this scale. A physicist proposed cooling the lava front with seawater.
I can just imagine the skepticism in that room. Sir, there's a wall of molten rock. We'll grab a hose.
I'm sure it sounded desperate. And it started small, with pumps from fishing boats. But they noticed something. The water was cooling the lava enough to solidify it into a wall. They were using the eruption itself to build a barrier.
A man-made barrier out of solidified lava.
Right. But the local pumps weren't enough, so they escalated. The U.S. Navy flew in massive industrial pumps. The operation eventually pumped 5.7 million tons of seawater onto that flow.
There is one detail in the report about this that I can't get over. They realized cooling the edge wasn't enough. They had to core the interior of the flow.
Right, because if the inside is still liquid, it'll just break through the crust. They needed to get water deep inside.
So they sent in bulldozers.
Yes.
Bulldozers driving onto the cooling crust of an active lava flow to lay pipes.
It is terrifying to think about. They were driving on this rubbly, sharp lava. The crust was solid enough to hold a bulldozer, but just a few meters underneath, the rock was still 1,000 degrees and flowing.
If the crust broke.
The driver is gone, instantly. It was the definition of high stakes. They laid pipes 200 meters back from the edge, pumping water directly into the heart of the flow.
And the amazing thing is, it worked.
It did. They saved the harbor. About 400 homes were buried, but the harbor mouth was preserved. In fact, the new lava actually made the harbor better, more sheltered.
That's a victory for human stubbornness, if I've ever heard one.
It proved a fundamental point. Lava is not magic. It's a fluid with physical properties. If you can remove heat energy, you can change its viscosity. You can influence it.
So that handles the lava. But in the 21st century, the problem isn't always something you can spray water on. Sometimes the problem is 30,000 feet in the air.
Ah, yes. 2010.
The eruption with the name that defeated news anchors everywhere. Eyjafjallajökull.
Yeah, just call it E15. This event was fascinating because, geologically, it wasn't a huge eruption. It was moderate.
But it grounded 100,000 flights. It cost the global economy billions.
And that shows how hazard is defined by more than just the size of the explosion. E15 was a perfect storm. First, the magma interacted with the glacier's meltwater. That blasted the magma into incredibly fine glass-like dust.
Exactly what jet engines hate.
Exactly. It melts in the hot turbine and coats the engine parts in glass. But the second factor was the wind. The jet stream was blowing directly from Iceland toward continental Europe.
It was like a dedicated ash delivery system for the European Union.
Precisely. Now, contrast that with the Grímsvötn eruption just 1 year later, in 2011.
I barely remember that one.
Most people don't. But the data shows Grimsvötn was actually a larger eruption, more powerful. It pumped out more material per second.
So why did it shut down the world?
The weather. The winds were blowing differently, carrying the ash away from major flight paths, and the eruption was shorter. It shows that a volcano's impact is determined as much by the weather report as by the magma chamber.
Speaking of which, we need to talk about the recent activity. The Reykjanes Peninsula, right near the capital, has woken up.
We've entered a new cycle, but before that, in 2014, we had the Holuran eruption, and that introduces another invisible killer.
The gas.
Holuran was a monster, the largest lava flow since 1783. But it was in the remote highlands, so no houses were threatened. However, it released massive amounts of sulfur dioxide, SO2.
The report says towns 100 kilometers away had to shut down.
Yes. The air turned toxic. People had to stay indoors with windows taped shut. It's a reminder that a volcano can hurt you without ever touching you.
And then came 2021, Fissure. This is the so-called tourist volcano, right?
It was accessible, yes, but for the engineers, it was another test of the 1973 playbook. They built diversion dikes, large earthen walls, to try and keep lava out of certain valleys.
Did it work as well as the water cooling?
Well, this is where nature threw a curveball. At first, the lava was that chunky, slow, lava the walls held, but then the eruption chemistry shifted.
It changed its personality.
It did. It started producing pahuho. This is smooth, ropey, very fluid lava. It moves much faster.
And I'm guessing that's much harder to stop with an earthen wall.
Much harder. It easily flowed right over the barriers. It shows that while our models are better, the Earth is full of variables we can't fully predict. You build a wall for one type of lava, and the volcano sends you another.
So we've covered fire hoses, bulldozers, gas masks. But there's one more layer to this survival kit. It's less exciting, but arguably it saves more livelihood.
You're talking about the NTI.
The Natural Catastrophe Insurance of Iceland.
It might sound dry, but this financial structure is the only reason you can get a mortgage in Iceland.
It was set up right after that 1973 eruption.
Yes. The government realized private insurance companies would never touch these risks. A house in the path of a volcano is uninsurable.
So the government stepped in.
They created a mandatory pool. If you buy fire insurance for your house, which is required by law, you must also buy catastrophe insurance. It's bundled.
So the person in a safe apartment in Reykjavik is subsidizing the person living next to the volcano.
Exactly. It's a solidarity system. The premium is tiny because everyone pays it. It spreads the catastrophic risk across the entire population.
But I was looking at the fine print. It covers the buildings and its contents, but
it doesn't cover business interruption. And that's a huge deal if you run a hotel and the volcano doesn't hit you, but it cuts the road so no tourists can come for 3 months.
you get zero.
Zero. Your income is gone, but the building is fine, so the insurance doesn't trigger. It's a major vulnerability.
And cars.
Also not covered. If you leave your car in the path of the lava, hopefully you have good private insurance.
Still, without this system, the economy would collapse after every major event.
Completely. It's a system designed to ensure a natural disaster doesn't become a permanent economic fatality.
Wow.
It allows society to bounce back.
It really changes how you define resilience. We think of concrete and steel, but in this case, resilience is also a bureaucracy. It's a tax code.
That's a great way to put it. You can't stop the plates from moving. You can divert a lava flow, maybe, but you can't turn off the mantle plume. So you build a society that's flexible. You build diversion dikes, yes, but you also build a financial safety net.
So looking at all these sources, it seems like they have this under control. They have a system.
They do, but there is always a but with volcanology.
The big ones.
We have to respect the timeline. We have been talking about events from the last 50 years. In geological time, that's a blink. The sources mention the Laki eruption of 1783.
That wasn't just a bad week for air travel. That changed the global climate.
It released so much gas, it caused a haze across Europe. It lowered global temperatures, it caused crop failures, famine. It may have even helped trigger the French Revolution.
And the sources suggest these massive events recur every 250 to 1,000 years.
We are within that window.
That's the thought that keeps me up at night. In 2010, the modern world was brought to its knees by E15, which was a moderate eruption.
Correct. We struggled with a medium-sized event.
So the question is, are we actually ready for a repeat of 1783? If a moderate eruption stops 100,000 flights, what does a massive flood basalt do to our global food supply?
That is the question the geologists ask. We've adapted well to the normal chaos. But the geological history shows us the Earth is capable of much, much more.
Something to chew on the next time you're sitting on the tarmac waiting for a flight.
Indeed. Respect the magma.
That is all for today's